Hello, you're welcome. Okay, so we'll continue from where we stop, right? This is another topic before us is alternating current. All right, so now what is an alternating current? Okay, alternating current is defined as a current that changes magnitude and direction with time. Now, the magnitude is talking about the size or the quantity, okay? So an alternating current changes magnitude. So the value of the alternating current actually changes, and the direction of the alternating current changes as the time progresses. Okay. So as the current vary periodically, so does the voltage also vary. So which simply means that an alternating current can actually be represented, okay, in form of a wave, okay, wave equation. So it actually varies periodically like a wave. I'm gonna draw the graph of an alternating current. So this is the horizontal axis. Okay, this is the vertical axis and this is the horizontal axis. So it actually, the current actually changes. As you can see, it changes at this point. Okay, here it is positive, then it changes magnitude, becomes negative, right? This just the graph of a wave, right? That's how an alternating current is. So that means the current, all right, varies with time, changes with time. Now, one thing is that, okay, both the alternating current, all right, because both current and voltage, right, they work hand in hand. So if the current actually changes, then voltage will change. Why? Because we know according to Ohm's law, right, voltage is related to current by IR. So as the current changes with time, so does the voltage also change with time. All right, so this graph of current current against time, and of course the alternating voltage against time. So I hope that is well understood. All right, let's proceed. Okay, so now let's look at the equation of an alternating current. Okay, so the equation of alternating current is given as, for I is given as I 0 sine omega t. Then for V, for voltage, is given as V0 sine omega t. Now, this equation, okay, I have given you when we actually treated the wave. The same equation of a progressive wave, that is what we use, okay, for alternating current, okay? While the amplitude in that equation of wave here represent I0. This I0, okay, let's look at the parameters, all right? Where I0 is the peak or the maximum current. So as you can see, the peak, this is the maximum, okay? The maximum current from here to here, this the maximum current from the mean point to this maximum point, okay? This represent I0, the maximum current. All right, the same thing, this is the maximum voltage, that's what you get here. Okay, so you call the maximum current or the peak current, right? The omega represent the angular frequency, you already know that. Okay, V0 is peak or maximum voltage. So now we'll talk about the root mean square value, all right, of an alternating current. So don't forget, so if I want to represent the equation of an alternating current, right, it will be this is for the equation of the alternating current, right? So now remember, this equation shows that the phase angle, if I'm using this equation, shows that the phase is equal to 0. But a situation where the alternating current, okay, has a phase angle, right, has a phase angle, then the equation now have to include the phase. So it's going to be I0, then sine bracket omega t, All right. Now plus phi, the phase angle. Now we're going to talk about, okay, the instances and the condition that will warrant an alternating current to have a phase angle. But if the alternating current doesn't have a phase angle, this is how we represent the equation. All right. So now we look at what is known as the root mean square value of an alternating current. Right. The root mean square value of an alternating current or voltage is the direct current that will produce equal heating effect. Okay, the direct current. Now remember, for a direct current can be measured directly. Every direct current has a steady voltage. Okay, DC has steady voltage. The voltage or the current is always steady throughout the time. So it is easy for you to measure, all right, a DC with a measuring instrument, ammeter, all right, to get the value. But AC cannot be measured, okay, using the using ammeter, okay, or direct current measuring instrument. The reason being that since the current actually changes, let's say at some point it is 1 volt. Before you know it becomes 2 volt, and this change is actually is very fast, running at sometimes at a frequency of even 60 hertz. Right, frequency of 60 hertz is very fast, okay, in such a way that you cannot really, okay, observe the change. So it's not a very slow change, it's a very fast change. Okay, so now if I really want to measure alternating current, how do I measure it? All right, to measure alternating current, I can't measure it directly. Why? Because the current changes. Okay, but rather I can measure it based on the heating effect it produces that is equivalent to this heating effect. All right, so I will actually use its heating effect. So that heating effect that alternating current can produce is based on the average. Okay, so it's based on this the root mean square. So the only way I will have to measure alternating current is to measure its root mean square. Its root mean square value. All right. So for current, we call it IRMX. IRMX, root mean square value, because we cannot measure the alternating current, all right, individually, because it changes, the value changes, but rather we can measure its root mean square value. So which actually tells us it's equivalent to the heating effect, okay, that is equivalent to its DC value, if that actually makes sense. So now the root mean square value of an alternating current, okay, of an alternating current, if you want to measure it, is always given by the formula, the maximum current or the peak current, all right, divided by the square root of 2. All right, and the same thing happens to voltage. If you want to get the root mean square value of alternating current voltage, okay, that's going to be the maximum value of the voltage divided by the square root of 2. Okay, so if I should have, let's say, an alternating current equation, okay, probably given as 2 sine, okay, 20t. All right, and you're being asked to find the please pardon me, this is I not I0, right? Okay, and you're being asked to find, okay, the IRMX. You're being asked to find the IRMX of this particular alternating current. Simple. Remember, these two represent the I0, right? So the answer is going to be this 2 divided by the square root of 2. All right, so of course, if you should simplify this, okay, you should have as 2 root 2 all over root 2 times root 2. I'm just rationalizing, okay. Root 2 cancels root 2, that's root 2 This is sod. But just in case you don't know what I did, just use calculator and get your answer, right? If you find the square root of 2, that's going to be 1.4 ampere approximately. So you can use calculator to do this in case you don't understand what I did. All right, so please take note of that. That is how to evaluate the root mean square value of an alternating current. All right, so let's proceed. Okay, so these are the formula I gave you. Okay, IRMS is I0 all over the square root of 2. VRMS is V0 all over the square root of 2. Now let's proceed. So we are going to talk about reactance. All right. Now, what is reactance? Now, reactance is defined as the opposition to the flow of alternating current, which is offered by a capacitor or an inductor. All right. Remember, we have, when we studied direct current, current electricity, we have what is known as resistance. So resistance is the opposition to the flow of direct current, okay, which of course is being offered, okay, by a resistor. It's the resistor that actually causes or offer that opposition. But when we come to alternating current, okay, the flow, the resistance or the opposition to the flow of alternating current is not called resistance, but rather it is called reactance, okay, and it is inductor and capacitor that provides reactance. So now let's look at different types of reactance. We have inductive reactance, okay. Now an inductive reactance is actually being provided by an inductor. Now when an inductor is connected across an alternating current, right, the voltage leads the current by 90 degrees. So now you now see this is the situation where phase angle actually enter into alternating current, okay. Whenever you connect an inductor, okay, in the pathway of an alternating current, what happens is this: there's going to be a lag, there's going to be a difference in phase between the current and the voltage. So you discover that the voltage will be leading the current by 90 degrees, okay. So the voltage will be ahead of the current by 90 degrees as shown in the diagram below. Let's look at the diagram, right? Okay, so this is the diagram. So this diagram is called an Argand diagram, which shows that when an inductor is in, all right, a component in alternating current, the voltage VL is, okay, because it's vertical while the current is horizontal. That is, the angle between them is what? 90 degrees. So I can write that in form of an equation, right? So if I want to write that, now that simply means that for current doesn't have any phase angle, right? Because current is, let's say current is 0. So current, if current is 0, right, that's the equation of current alternating current, because I0 is an omega t, all right, which shows that the phase angle of current is 0. So why? Because now if voltage is leading the current, all right, the voltage leads the current by 90 degrees. So that means for voltage, all right, the voltage now is gonna be written in phase angle, that is V0 sine, okay, omega t, then plus the phase angle, because the phase angle for this is 90 degrees. All right, of course, 90 degrees in radians is pi all over 2, right? Plus pi all over 2. So if I'm writing the equation of voltage, okay, in an alternating current that has inductor, this is how I will write it, because there's going to be a phase angle, right, for voltage. So please take note of that as we proceed. So this is for an inductor, right? Now so how do we now calculate the inductive reactance? Remember, inductive reactance is the opposition to, okay, to the flow. Okay, so now, first of all, before we go to capacitive reactance, so what is the formula for inductive reactance? This is just what I just gave here, all right, is just the equation, all right, but what is the formula for inductive reactance? The formula for inductive reactance. Now, inductive reactance, is represented by the symbol XL. Inductive reactance XL of an inductor in an alternating current circuit is given by omega L. Angular frequency multiplied by L. Already, when we treated wave, we know that angular frequency is given by 2 pi f. 2 pi f. So it's going to be 2 pi FL. So this is the formula for inductive reactant SL. Okay, so please take note of this. So this symbol SL is inductive reactance. Okay, so that is it. Now we look at please take note of the formula. We now look at the next reactance, which is capacitive reactance. Now, capacitive reactance is being provided by a capacitor. Now, when a capacitor is connected across an alternating current source, the current leads the voltage by 90 degrees. So the current now this time around is ahead of the voltage by 90 degrees. Okay, so that means invariably now, if I should write that equation, okay, for capacitive reactance, if I write the equation of when you have a capacitor being connected to an AC source, right, you discover that the current now is the one that is actually leading. Okay, the current now is leading. So the current leads now. So if the current leads, that means the voltage lags. The current leads by 90 degrees. So if I should write this for current, then definitely for voltage, that would be the first angle is gonna be 0. Okay. But a situation where, just in case you see that in exam, a situation where, okay, for current I didn't put the phase. I have, let's say, actually wrote it this way: I0 sine omega t. Okay, remember the voltage is lagging me. So if I didn't put the first angle, so that means for voltage now I have to subtract. Okay, excuse me. For voltage now I have to subtract. That's V0 sine. Okay, so this shows lag. Omega t then minus pi all over 2. Okay, so this shows that the voltage lags behind the current by 90 degrees. Okay, I hope that is well understood. All right, so now the question is, how do we actually write what's the formula for the capacitive reactance? Now the capacitive reactance, the symbol I'm gonna use SC. All right, the capacitive reactance XC is given as this time around 1 all over. So 1 all over omega C. So which of course we know that omega is 2 pi f. So that means capacitive reactance is going to be equal to 1 all over 2 pi fc. So please take note of that. Inductive reactance is 2 pi fl, while capacitive reactance is 1 all over 2 pi fc. All right, so now we go to the combined reactance. Okay, the combined reactance is called impedance. What's an impedance? Impedance is the total opposition to the flow of current offered by resistor, inductor, and capacitor. So when you combine all these components, as you can see in this diagram, the total opposition they give, the total opposition given by this component, all right, is known as the impedance. Okay, we get impedance when we get the total opposition, right? So which simply means that if I want to write based on Ohm's law, Okay, that simply means that if I want to write the formula based on Ohm's law for an alternating current, I will say that, okay, the voltage of an alternating current is equal to okay, of course, the voltage of an alternating current is given as the VRMX, right? Okay, then it's equal to the the current of an alternating is IRMS, okay, then times the resistance, and the resistance now is Z, which of course, so why Z now is talking about the total opposition, which of course is known as the impedance. All right, so that means if I want to get the impedance from this formula now, okay, for you to get the impedance Z, just for you to, okay, get the root mean square value of the voltage divided by the root mean, okay, square value of the current, VRMX all over IRMX. Okay, so now the question is, we know very well that what actually constitutes the impedance Z, right? Z is the impedance. What constitutes the impedance is both the resistor, right, is capacitor, right, inductor, and of course resistor. Everything, okay, is what contains. So now how do we actually write the formula for that total opposition impedance? Now I'm going to draw how their diagram, okay, how all of them are related. Remember, for resistor, anytime alternating current, I'm not talking about, okay, the one of resistor. Anytime an alternating current is being connected across a resistor, all right, there is no lag. Voltage and current doesn't lag. So I can use for resistor, all right, I can use horizontal line to represent the resistor, okay, since there's no lag for resistor. So this horizontal line represent resistor. You know, for an inductor, okay, an inductor, there is, okay, for an inductor, that's of course inductive reactance, right, has in this diagram, okay, is positive vertically, okay, is in the vertical direction, that is vertical direction, okay, positive vertical direction, and of course the capacitor. So this is the diagram that represents these three components, okay, inductive reactance, capacitive reactance, and resistor. And having that both capacitor, all right, reactance and inductive reactance are in the same direction but opposite, all right, so their total reactance, okay, total reactance, let me, you know, okay, based on vector, right, so the total reactance now is going to be equal to, I'm going to subtract the acting in opposite direction, that is XL minus XC, okay, then of course the resistance, okay, already we know the resistance, being the horizontal, which is R. Okay, so now impedance is going to be, as you can see, impedance is going to be the resultant of these two. Now the resultant of these two, remember, okay, if I should draw this now, I use, let's say, one, okay, this vertical represents the reactance, okay, which is vertical, and we know that the horizontal now, okay, excuse me, reactance, the horizontal we know is the resistance, vertical is the reactance. So now the impedance, as you can see, this is vertical and horizontal. So the impedance is going to be the resultant of this and this. And according to by Pythagoras theorem, okay, if I want to actually get the resultant of this, since they are perpendicular to each other, I'm going to apply Pythagoras theorem. Okay, so now this now becomes, okay, if I believe that in vectors, you know that, okay, if I want to get the resultant of two vectors, all right, perpendicular to each other, I will apply Pythagoras theorem. All right, so now this becomes the impedance. So by virtue of Pythagoras theorem, the impedance now becomes, is going to be equal to the square root of, okay, the reactance, which of course is SL minus XC all square, then plus the resistance R square. All right, so the impedance, total opposition to the flow of current in uh, um, an alternating current circuit, all right, is given as this. Okay, let me write it again. Impedance is going to be equal to the square root of the reactance. The reactance is XL minus X all square, then plus the resistance square R square. So I hope that is well understood. All right, so done. So now we'll talk about resonance. Okay, resonance in an alternating current circuit. Resonance occur in an AC circuit at a frequency, okay, at a particular frequency where the inductive reactance is equal to the capacitive reactance. Okay, now remember, every alternating current circuit will have frequency, okay, because it's alternating. There's a frequency of alternation. So there's a frequency. As the frequency changes, okay, there's going to be a point where inductive reactance becomes equal to capacitive reactance. At that point, we say resonance have occurred. All right, now this resonance causes maximum current to flow. A situation where inductive reactance and capacitive reactance are equal, maximum current will flow. Why? Because they will cancel out to give zero. Remember, okay, the total reactance, all right, is always given as SL minus XC. If they are equal, okay, they will cancel out. Then that means the reactance now becomes zero. Okay, that opposition based on reactance becomes zero. So that circuit will only be resistive. Let me illustrate what I mean. Okay, let's go to the board. All right, so if a situation where SL, all right, is equal to SC, now you discover that this whole, okay, this whole SL, okay, minus SC becomes what? Zero. And this happened at right, at resonance. This happened at resonance. So because of that, then you now discover that the impedance now have reduced to just the square root of R square. Why? Because this is already zero. So the impedance now becomes just the resistor. So that means opposition to the flow of alternating current now has reduced drastically. There's no opposition, there's no reactance again in that circuit. Okay, and because the opposition to the flow of current has reduced, so that is, at that point you now have maximum current. Okay, maximum current flowing through the circuit. So maximum current flows through a circuit that is on resonance. Okay, because inductive reactance is equal to capacitive reactance. So please take note of that. All right, so the frequency at that, where that particular frequency that resonance actually occur is known as resonance frequency, and I'm going to show you. Okay, we are going to derive the formula for resonance frequency. Okay, so how do we evaluate the formula for resonance frequency? Let's look at resonance frequency. Let's look at resonance frequency. Okay, let me use F0 to represent that. Okay, now how do we get to now at resonance? We know very well that inductive reactance SL is equal to capacitive reactance XC. Okay, Inductive reactance is, of course, you know it is 2 pi FL. All right, capacitive reactance is 1 all over 2 pi FC. All right, so at that point the F is resonance, that's F0. So cross multiplying, if I should cross multiply, of course this all over 1, right? 2 multiplied by 2, that's going to be 4. F multiplied by F, that's F, okay, F0 square, right? Then okay, I've not, pi multiplied by pi, right? Pi square. Okay, then L multiplied by C, that's LC, is equal to 1. So that means F0 square is going to be equal to 1 all over 4 pi square. 1 over 4 pi square, okay? Then LC. So now for me to get resonance frequency, I'm going to find the square root of all this. Square root of 1 all over 4 pi. 4 pi square LC. Okay, so my resonance frequency is going to be equal to the square root of 1 is 1. The square root of 4 is 2. The square root of pi square is pi. Then of course, now the LC, I have to put the LC inside the square root. So this is the formula for resonance frequency. Resonance frequency, 1 all over 2 pi, the square root of LC. All right, so I hope that is well understood. So now let's look at some question. At what frequency would the capacitor of 2.5 microfarad be used in a radio circuit to have a reactance of 250 ohms? Okay, so this is a capacitor. So here we are dealing with capacitive reactance. So we are going to be solving question here now. All right, capacitive reactance. So according to the question, the capacitance is a the capacitance, right, is 2.5 microfarad. Okay, now this capacitance, of course, is used in a circuit that offers the reactance of 250 ohms. Okay, so now the question is, what are we looking for? What is the frequency? Okay, know the formula now. Capacitive reactance is given as 1 all over 2 pi FC, right? So capacitive reactance is 250 equal to 1 all over 2 pi. All right, then F times the capacitance, which is 2.5, times 10 raised to the power of minus 6. All right, so if we cross multiply, I'm going to have 250 times 2 times 2.5. Okay, so let me possibly get a calculator. Okay, here we go. I'm cross multiplying now. I'm going to have 250, right, times 2 times 2.5. Then of course pi is 3.14. I still need to multiply by 3.14. Right, 3925. Of course, 10 raised by minus 6 is divided, this 1 all over 1 million. Okay, so I have to divide this by 1 million. Okay, yeah. So everything now is giving me, right, along with F. Okay, so after cross multiplying, that's 0.003925. 0.003925 F, all right, is equal to 1. So now F is going to be equal to 1 divided by 0.003925. Okay, so let's do that division. 1 divided by 0.003925. What do we have? So approximately 254. So the frequency is 254 hertz. All right, so I hope that is well understood. So that's the frequency of the alternating current. Next question. Okay, here I have a question. It goes like this: the current through a resistor in an AC circuit is 2 sine omega t. So this is the current equation, okay? And this current equation is through a resistor, and of course there's no phase angle because it's through a resistor. This equation determine the DC equivalent of the current. So the DC equivalent of the current is the IRMX. Okay. The DC equivalent of the current is the IRMX. Which of course is giving us I0 all over the square root of 2. So from the equation I can see that I0, okay, is 2. So that's going to be 2 divided by the square root of 2, right? I think I did this before, which, all right, should give you this 1.4. So you can use calculator to confirm that, right, as we proceed. All right, so here I have another question. A coil of this should be impedance, okay? That's a mistake here. This should be a coil of reactance, okay? So a coil of inductance, this Henry 0.07 Henry. Henry is the SI unit of inductance, so please correct this. It's a mistake, right? A coil of inductance 0.007 Henry. A resistor of resistance 8 ohm and a capacitor, okay, of capacitance 0.001 farad are connected in series, okay, to an AC, in series to an AC source of frequency 500 pi hertz. If the RMS voltage across the core, okay, the resistor and the capacitor is 30 volt, 20 volt, and 70 volt respectively. So what are we looking for? Draw the vector diagram to illustrate the voltage across the components. Okay, so let's look at how we draw the vector diagram, right? If the RMS voltage across the core, so for the inductor, the RMS voltage is 30 volt. For the resistor, that is 20 volt horizontal, remember. For the capacitor, okay, 70 volt. Okay, that's downward. Okay, so now let's go by that. Let's start with, okay, the I part of the question. Let's draw the vector diagram. Okay, so let me clean up. Let me clean up, all right? Okay, so vector diagram, here we come. Remember, alternating voltage. Okay, first of all, for resistor, right? For resistor, the alternative voltage for resistor, okay, is gonna be VR. Let me just write that as VR. The alternative voltage for resistor, VR, okay, there's no phase angle. So that is 70, okay, according to the question, 70 volts, right? Is it 70 volts? I have coil resistor, okay, no, 20 volts. Coil resistor and capacitor, 20 volts. So 20 volts. Now remember, for inductor, all right, whenever inductor is connected across alternating AC, the voltage leads. So this one now vertical, this one that is leading, okay, of VL. All right, so this one is for the inductor, and now from the inductor is a coil, right? That's 30 volts. So this one is 30 volts. Then for capacitor, remember capacitor lag the voltage. Whenever a capacitor is connected across an AC, the voltage always lag the current. So this one downward here is for capacitor, and that is 70 volts. So this is the vector diagram, right, or the Argand diagram of that represent that. Okay, so number one question has been taken care of. Let's now look at number two. Calculate the RMS voltage of the source. Okay, RMS voltage here will come. Now, how do we get the RMS voltage? Okay, now no equation is given. Now we read the question. The capacitance or the inductance, right, is 0.07 Henry. The resistance is this. The capacitance is this. Okay, are connected in AC source, and the frequency. Okay. Okay, so if the RMS voltage across the core, the resistor, okay, so it has already been given to us now. The question is calculate the RMS voltage of the source, okay, of this, the RMS voltage, of the source, okay. If the RMS voltage across the, okay, this are the RMS voltage across the core. So we are looking for the RMS voltage of the source. Very okay, simple. So we can get it from here. So this one. This represents the RMS voltage across the resistor. This represents the RMS voltage across the capacitor, and this represents the RMS voltage across the inductor. So the combination of all of them, both the resistor, inductor, and capacitor, give me the RMS voltage of the source. Okay, so that means VRMX is gonna be the resultant, all right, or this, okay, the vectorial sum of this. And do you know how we do that? It will be in terms of Pythagoras theorem. All right, it's gonna be VL minus V all square, right, then plus R square. So now VRMX or the source becomes gonna be equal to VL, okay, that is how many? That's 30 volts, right? So I'm gonna have 30 minus VC 70 all square, then plus R square 20 square. All right, so this is gonna be equal to this square root of 30 minus 70. What do we have? That's 40, right? Minus 40. So this is gonna be minus 40 all square, then plus 20 square. Okay, so it's gonna be equal to 40 square. All right, so give me 1600 minus 40 square, right, is 1600. Then 20 square is 400. So which eventually gives 2000, right? The square root of 2000. So let's see, 2000. All right, the square root 44.7. 44.7. All right, volts. That is the VRMX. All right, that is the II part of the question. Then okay, so we are looking for both. Calculate the RMS of the source, RMS current in the circuit. So we are looking for the RMS current in the circuit. Okay, so now for us to find the RMS current, okay, remember the VRMX is, the connection is VRMX, okay, is equal to IRMX, right? Then multiply by the total opposition, which is impedance. So that means for me to get IRMS now, it's going to be equal to VRMX, right, then divided by the impedance. Already we've gotten VRMS, which of course is 44.7, all right? Then I have to divide it by the impedance. And of course, you know how we do the impedance, okay? All right, so divide by the impedance. You know what the impedance will be? All right, bracket SL minus XC all square plus R square. Okay, so we have to calculate them one after the other. I have to calculate SL, I have to calculate SC. Let's see. All right, XL, of course, you know, is 2 pi FL. All right, so let's do that. I have, okay, the pi, the F, the frequency. Okay, according to the question. Where's the question? Let's go. All right, the frequency is 500 pi hertz, right? And 500 pi hertz, and of course the inductance is 0.07 Henry. So what I'm having here now is going to be equal to 2 times, okay, pi, which is 3.14, right? Approximately, then multiply by the frequency, okay, which is 500 pi. 500 pi. Okay, this is really pretty long, so 500 pi times 3.14 again, then times the inductance now, which is 0.07. All right, so use calculator and do that. Then for the SC, all right, you know what the SC is. That's going to be 1 all over 2 pi FC. All right, so it's going to be equal to 1. Okay, so all divided by 2 times 3.14. All right, then times the same pi, 500 pi, right? You can just put the value of pi there. Then times the capacitance. What was the capacitance? 0.00. Okay, so calculator, use calculator and do that, and you will, after getting the value of this, get the value of this, put it inside this formula, and so this is gonna be a kind of a class work for you now, right? put inside this formula and you're good to go. Okay, put inside this formula. Do this, okay? Put inside that formula, evaluate it, and you have your answer. All right. Okay. And finally, okay, what's the next question? The next question, okay, power dissipated in the circuit. Power dissipated in the circuit, right? Power, don't forget, it's always giving us current. So that's going to be IRMX times VRMX. So whatever you have as your IRMX multiplied by VRMX, that gives you the power. All right. Then the next question is, write down the sinusoidal equation for the RMS voltage V in terms of time. All right, so for V, remember it's given as V0, right? Sine omega t. So that is the equation of the voltage. So the question, how do we get the V0, right? Remember VRMX. Okay, it's always given as V0 all over the square root of 2. So that means V0 now, the peak voltage is going to be equal to the square root of 2, all right, multiplied by the IRMX, which we have, multiplied by VRMS, which we calculated to be 44.7, right? So you do that, that's square root of 2 times 44.7, okay? So you can actually evaluate that. So after evaluating that, now just put it inside this, all right? Inside this, and that's all. That gives you the equation. All right, so as simple as that. I think that should be all. That's all. All right, so take your time, make sure that you solve this question, okay? Take it to the end, go through the video again. It's just very simple, okay? Just know how to apply the formula and you're good to go. All right, see you in the next video. Thank you very much.